The first part of Chapter 8 was a review of statics. This second part of Chapter 8 is new material that uses your ability to find beam reactions and introduces us to internal forces and moments within a beam. Here's a simply supported beam with a point load. Let's imagine what would happen if we were to slice the beam vertically at some point close to R sub A. We'll draw a free body diagram of the left-hand portion of the beam. R sub A is going upwards, so there must be an equal and opposite force going downwards. We'll call this vertical load V. In this beam, V equals R sub A. If the loading were different, then the value of V would be different. If all we had were the two forces, then the segment of the beam would want to rotate. To counter this rotation, there must be a moment at the slice. We'll call this moment M. In this beam, M equals V times the distance to point A. If we slice the beam to the right of the point load, we'll still have an internal vertical shear force and an internal moment. The signs might change, but the beam is still resisting the applied loads by developing internal forces and moments. We can graph the internal shear loads and moments to see where the values are the greatest. In the next few chapters, we will use the largest values of V and M to calculate shear stress and bending stress in beams. If you know how much stress is in a beam, you can compare it with how much stress the material can handle safely, and then determine whether the beam is strong enough to carry the load. To start, we'll draw construction lines below the load diagram wherever the load changes, either an applied load or a reaction force. Leave some room in your notes below the shear diagram because later we'll come back and add a moment diagram. What we do is step across the beam from left to right. If a force on the beam is going up, then we go up on the shear diagram. If a force on the beam is going down, then we go down the same amount on the shear diagram. Here we start at point A with an upward reaction force of 10 pounds. Starting at 0 on the shear diagram, go upwards 10 pounds. There are no more forces on the beam until we get to the midspan, so the internal shear force in the beam remains at 10 pounds. Draw a horizontal line across to the midspan. There's a downward applied point load of 20 pounds at the midspan, so we go down 20 pounds. It's simple arithmetic. 10 pounds minus 20 pounds takes us to minus 10 pounds. Moving further along the beam, there are no loads until we get to point B, so the internal shear load remains at minus 10 pounds. Draw a horizontal line over to point B. Now we have an upward reaction force, R sub B, of 10 pounds. So we go up 10 pounds to get to 0. It's easier to read a shear diagram if it's shaded in. It's a good idea to mark the values of the shear load on the shear diagram because it will make it easier to draw a moment diagram later. If we shift the point load away from the midspan, we will still get two rectangles in the shear diagram, but the reaction forces are not equal to each other. So one rectangle is taller than the other. Go up 8 kilonewtons, across to the point load, down 12 kilonewtons to minus 4 kilonewtons, across to point B, then up 4 kilonewtons. Since 8 kilonewtons is greater than 4 kilonewtons, the maximum shear load is between point A and the applied point load. If this beam exceeds its allowable shear stress, this is where the failure will occur. What if we have more than one point load? We will end up with a series of steps on the shear diagram. Go up 15 kips, across to the first point load, down 10 kips to 5 kips, across to the second point load, down 10 kips to minus 5 kips, across to the third point load, down 10 kips to minus 15 kips, across to point B, and up 15 kips to 0. If this beam exceeds its allowable shear stress, the failure could start at either end, where the maximum absolute value of the shear load is 15 kips. A uniform distributed load is like a series of small point loads placed really close together. So the steps merge into a continuous slope. We go up 20 kilonewtons and then down at a constant rate of 4 kilonewtons per meter until we get to minus 20 kilonewtons at point B, and then come back up to 0. Here's a more interesting loading case. We have a uniform distributed load that doesn't stretch across the entire beam. First, draw an equivalent load diagram off to the right to figure out the reaction forces. I recommend writing your equations under the equivalent load diagram so you can leave space under the actual load diagram free for your shear diagram. Once you have the reaction forces, draw construction lines below the original load diagram. Go up 180 pounds, then straight across to the beginning of the distributed load. Now go down at a diagonal at a constant rate of 100 pounds per foot until you reach point B, then up 420 pounds to 0. If this beam exceeds its allowable shear strength, it will fail at point B because this is where the absolute value of the shear load is greatest. The next step is to draw moment diagrams. We need moment diagrams to figure out the bending stresses in beams. Here's the key. The value of the moment diagram equals the area of the shear diagram up to that point. The area of the shear diagram is positive if it's above 0 and negative if it's below 0. First, draw construction lines below the shear diagram wherever the shear diagram changes its value. We'll consider a little portion of the shear diagram, say the first linear foot from the left end of the beam. The area is 10 pounds times 1 foot, which equals 10 foot-pounds. Draw a diagonal line ending at 10 foot-pounds. Now consider more area of the shear diagram. At a location of 2 feet, the area is 20 foot-pounds, so we continue our diagonal line up to the right. As we consider more area, the value of the moment diagram keeps increasing. At 4 feet, the moment is 40 foot-pounds. At the midspan, the moment is 50 foot-pounds. The rest of the shear diagram is negative, so we subtract the negative area, which takes us back to a moment of 0, which makes sense because it's a roller support. There can't be any moment remaining in the beam at a roller support. Shade in the area of the moment diagram. Make sure you've marked the values where the moment diagram changes direction, and you're done. What happens if the moment value doesn't go to 0 when you get done? With a simply supported beam, there are two possibilities. If the end result is a tiny fraction of the other numbers, then it's just round-off error, and you don't need to worry about it. Otherwise, it's a clue that there's a mistake someplace. The most likely place for the mistake is in the reaction force calculations. You can draw a shear diagram using the wrong reaction forces, but you usually cannot draw a successful moment diagram if the reaction forces are wrong. This is a good thing because the answer tells you if you've made a mistake or not. There aren't a lot of engineering calculation methods that tell you if you've made a mistake. We'll review the rest of the shear diagrams and draw moment diagrams for each case. A point load that's not at the midspan will still produce a triangular-shaped moment diagram, but the location of the maximum moment will be shifted. Bending stress is a function of bending moment. So in these two cases, if the beam fails because its allowable bending strength is exceeded, then failure will occur at the point load. The beam with 3 point loads produces a circus tent shape with 3 peaks. The maximum peak is at the center load. We said before that if this beam fails in shear, it will fail at the ends. If it fails in bending, it will fail in the middle. Rectangles in the shear diagram produce triangles and trapezoids in the moment diagram. Triangles in the shear diagram produce parabolas in the moment diagram. The maximum moment of the beam at the right is the area of the left-hand triangle, which is 1/2 of 5 meters times 20 kilonewtons, or 50 kilonewton meters. Now we get to our interesting loading case. The first part of the shear diagram is a positive rectangle, so we head upwards at a diagonal. The area of this rectangle is 720 foot-pounds. The next portion of the shear diagram is a little positive triangle, but we don't know what the base of this little triangle is. The way we find out is by using the principle of similar triangles. This little triangle has the same shape as a bigger triangle. Therefore, the ratio of the height to the base of each triangle is the same. We find that the value of x is 1.8 feet. The peak of our moment diagram is 720 foot-pounds, plus the area of the little triangle. I find it helpful to calculate each value of v and m off to the side as v1, v2, v3, m1, m2, m3, and so on. The new m value equals the previous m value plus or minus the additional area from the shear diagram. Finally, we subtract the area of the right-hand triangle to get back to 0.